Now we are going to look at our second example, whereby we are going to look at the function of cos omega t. Now, to solve this, there's two methods that we are going to look at. There's a brutal method, which I can say is a little bit longer than the second method, but both of them are quite interesting. Let's look at the first method first, the brutal method, or the longer version. Then after that, we'll look at the shorter version, and you can choose which method you want to solve this function. So let's write down. We want to look at the Laplace of cosine omega t, which is equal to integrating between 0 to infinity e to the minus st times our function cosine omega t dt. Now, to solve this, we need to use integration by part. And remember from calculus, integration by part, what we want is the integral of u dv is equal to uv minus the integral v du. Okay, let me just put this in this box here. Okay, now we can pick u is equal to e to the minus st, then differentiating this du du is equal to minus s e to the minus st dt. Next, we can pick dv is equal to cosine omega t dt. So integrating that, we get v is equal to 1 over omega sine omega t. Now, let me just write down again our equation that we want is uv minus the integral v du. U here is e to the minus st. So just going to insert that. U is e to the minus st. And v was 1 over omega sine omega t, and minus the integral 0 to infinity. V, we have v as 1 over omega sine omega t times du. Du is minus s times e to the minus st dt. And now we can evaluate this. Evaluate this between 0 to infinity. And plug in our upper limit. We are going to have e to the infinity then here we are going to have 1 over omega sine infinity minus, and plug in our lower limit is e to the 0 multiplied by 1 over omega sine 0 plus, and we can pull this s and 1 over omega outside the integral. Then we're gonna have s over omega, s over omega, integrating this between 0 to infinity, and just rewriting, we have e to the minus st times sine omega t dt. Now, let me use a different color. E to the, okay, this one was e to the minus infinity here. E to the minus infinity will drive this equation to 0. This is 0. Okay, anything times 0 is 0. So, hence, the entire equation, all of this is 0. Okay? And sine of 0. Sine of 0 is 0. So, this sine here will drive this equation to 0. E to the 0 is 1, but anything times 0 is 0. Hence, this whole equation will be 0. So, now, since this whole equation is 0, the only thing that is left over is this part. And we are going to look at this part. Let me just rewrite that. Now, we can see that this equation is, we have s over omega integrating from 0 to infinity, e to the minus st sine omega t dt. Now, this equation is the Laplace transform of the sine function, this whole thing here. Because, remember, let's write our Laplace transform equation again. We say that the Laplace transform f of s is equal to, we are integrating between 0 to infinity, e to the minus st times a function f of t. Now here, our function f of t is equal to sine omega t. So hence, this whole thing is the Laplace transform of sine omega t. Okay? Now, but we want the Laplace transform of cosine omega t. If we integrate this sine omega t by part again, we are going to receive something that is very interesting. Let's just do that. So, now we have the Laplace transform of cosine omega t is equal to, we are taking just this and that, is equal to s over omega integrating from 0 to infinity, e to the minus st times the sine omega t dt. Integrating by part, we let u is equal to e to the minus st. So du is equal to minus s e to the minus st, and dv is equal to sine omega t dt. Integrating that will give us v is equal to minus 1 over omega cosine omega t. Again, we go through the process again, exactly the way we did the first part, whereby we want to substitute all this information into uv minus integral of v du. So our u is equal to, we have e to the minus st. Let me just put this in brackets so that I keep everything nice and tidy. And v, with v we have minus 1 over omega cosine omega t, and minus the integral between 0 to infinity. V is minus 1 over omega cosine omega t. Du we have minus s times e to the minus st dt. Okay, now we can evaluate this again, just like before. And to evaluate this, we can write this as we have minus omega. I'm just pulling it out because we multiply this with 1 over omega e to the minus infinity times cosine infinity minus our lower part minus 1 over omega e to the 0 cosine 0 minus we can pull again this s and this part outside our integral, which will give us s over omega integrating between 0 to infinity times e to the minus st times cosine omega t dt. And let me just shift this up a little bit so that I have enough space to write on. Now we can evaluate. E to the minus infinity will drive this whole thing to 0, just like before. So this whole thing will go to 0. Cosine of 0, this is 1, okay? And e to the 0 is 1, so here we are going to have minus and minus is positive, so plus 1 over omega. And here we are going to have minus s over omega. This one is just coming out here. And this part here, just like before, this is the Laplace transform of cosine omega t. Now we have something that is very interesting. So we can say that, okay, from the beginning what we found is we want the Laplace transform of cosine omega t, which we found from the beginning. Let me just go. We found it here, okay, this part here. I'm just going to rewrite it here. It's equal to s over omega times the Laplace transform of sine omega t. And we found the Laplace transform of sine omega t to be this variable, and this one. We are going to substitute that into this equation. So let me just do that. So Laplace transform of cosine omega t is equal to s over omega, going to open my bracket here, and I'm going to substitute the values that I found to be for the Laplace transform of the sine omega t, which is, we have 1 over omega minus s over omega times the Laplace transform of cosine omega t. Then I close this bracket. Okay. Then now I'm going to rewrite this properly, and just to try and clean it up. So the Laplace transform of cosine omega t is equal to, multiplying this out, I'm going to have sine over omega squared minus s squared over omega squared. I'm just multiplying s times s squared, omega times omega is omega squared, okay, times the Laplace transform of cosine omega t. Okay. Now I can take the like terms, this part, onto this side. So if I take it on the other side, I'm going to have the Laplace transform cosine omega t plus s squared over omega squared times the Laplace transform of cosine omega t is equal to s over omega squared. Then I'm going to factor out the Laplace transform of the cosine omega t. So we can rewrite this as the Laplace transform of cosine omega t times 1 plus s squared over omega squared is equal to s over omega squared. Then I want the Laplace transform of the omega t to be on one side, because that's what we want to solve. So I can divide through by 1 plus s squared over omega squared on both sides to get rid of this one. So we are going to have the Laplace transform cosine omega t is equal to s over omega squared divided by 1 plus s squared over omega squared. Now if I multiply through by omega squared, top and bottom, so omega squared here, let me just rewrite this properly. Let me take a different color. Omega squared here, omega squared here. That and that is going to cancel out. Omega squared is going to come here, and the other omega squared I'm going to cancel out with that. So hence the Laplace transform of cosine omega t is equal to s over omega squared plus s squared. So this is the Laplace transform of cosine omega t. I hope this is clear, and yes, it requires proper attention, regular mathematics, basic algebra, just basic manipulation, etc. But it's not difficult, apart from just going through your calculus and understanding that, okay, if you have a function that is multiplied by an exponential, you have to use your integration by parts. And next we are going to do the same equation. We are going to solve the same equation, but we are going to use a different method. You are at liberty to use whatever method you want to use, and I'll see you in the next video.